Hello, everyone. So, in this today's session, we are going to talk about one more problem characteristics, that is role of knowledge. Okay. So, by the end of this session, you will understand exactly why knowledge is not just helpful. So, it is the single most powerful tool an AI agent can use. So, think about this role of knowledge with respect to the so many problems we have seen so far. Supposing if I have asked you to find the exit of a giant maze, so how would you approach this problem to find the exit? Supposing you don't have maps, you don't have clues, you have zero information about the maze. So automatically what you will try to do, you would have to wander and try every corridor, all the possibilities. Supposingly, if I am giving you a clue that the exit is always in the northeast corner. So what would you do? So with this knowledge or the information, you would straight away walk to that northeast corner for exit. So that's exactly what knowledge does for an AI agent. It turns a slow, exhaustive, expensive search process into something fast, efficient, and elegant. So, we are going to explore different types of agents and we will build it step by step with work examples. Okay, so now let's begin, right? So, first of all, now with the title slide, we understood that so given a problem, the agent must have some knowledge about that particular environment. Then only it will be easy for the agent to find the optimal solution for the problem. Now, the core question we need to answer is how much does an AI agent need to know in order to solve a problem? Because if I take any kind of problem, so there are huge volume of information about that particular problem. So how much does an AI agent should know to get an optimal solution? So to understand this, there are three distinct levels. Okay. We will talk about three distinct levels. How the agent will know the or how much the agent should know about the environment. First one is the blind agent. So blind agent. The blind agent knows nothing beyond the problem definition itself. So what exactly it knows? It knows the starting state. It knows what action it can take. And it knows what the goal looks like. That's all. So if you take a maze problem, so what you might know, this is the entry point where you have to start. Might be you can tell if you bang on a wall, you might get yourself hurt. So if you find a door, then that is an exit. Something like this. This much information only the agent will know. So what the agent will do? It searches exhaustively. It tries all possibilities. So this will guarantee that it will find a solution if one solution exists. But it's very slow. How long it will take? Imagine for a problem like chessboard. How many possibilities you will try? So you like that we can define n number of problems. Okay. Second one is about the informed agent. Now this informed agent has some domain knowledge. So it knows something about the problem. That is the structure of the problem. Suppose if I talk about an 8 queens problem, it will know the chessboard is 8 cross 8. It will have the squares, every coin position. So it will know something about the problem. So rather than trying all the paths blindly, it will use the knowledge to search smarter but not harder. So compared to this blind agent, it is very faster, it will be more efficient and more practical. Now, the third agent, that is a knowledge-based agent. This agent has a deep knowledge about what the rich rules or the deep rules, the facts, the ability to do inferences from the information available. So, it doesn't search more efficiently. In many cases, it doesn't need to search at all. Like, for example, we have seen this Marcus problem already, right? In the previous sessions. Okay. So it can directly reason, deduce, and eliminate large portion of search. Okay. Example, in Marcus problem, we have to find out like whether is Marcus alive. See, we know that Marcus is a Pompeian. All Pompeians don't live for this so many above 150 years. Now it is 2024 AD. So with all these logics, directly we can conclude that knowledge-based agent will conclude Marcus is not alive. Okay. So the key takeaway from this agent or the knowledge agents, more knowledge equals less search. And less search means it's very fast, it's more efficient and more practical. So to go forward, I hope this blind, informed and knowledge-based agent is clear. Now we will talk about all these various agents with some examples for you. Okay. First, we'll talk about the blind search, that is no knowledge. Okay, which uses what we call this particular agent will use something called as uninformed search or blind search strategies. Okay, so it knows only about the initial state, actions, and goal state. So how does it work? The agent explores all possible states systematically. It has no preference for one path over the another path. Guaranteed to find a solution if one solution exists. But it's extremely slow and it's very costly because you have to search everything. So, what are the possible algorithms that can be used? First, the breadth first search. This agent explores all nodes at one depth level before moving to the next level. So we talked about water jug problem. Okay. So BFS guarantees the shortest path, but it checks eventually all the nodes. Okay. The second one is the depth first search. So rather than searching level by level, spreading out, the agent goes deep as possible down one path. So before backtracking, it tries the one full path downwards. Compared to BFS, it uses less memory because you don't have to store all the paths. But it might completely miss the shortest route because sometimes your solution might be at level 2. You might be at depth level 10, which is of no use. The third one is the uniform cost search or otherwise UCS. This one expands the node with the lowest total cost. Okay. So the agent does not know where the goal is, but it searches the node closest to the goal with lowest cost. So it's cost aware, but still direction is blind here. Okay. Suppose if you take the 8 puzzle problem with BFS alone, I mean applying BFS. So 8 puzzle is a 3 cross 3 grid problem. It will have the tiles arranged 1, 2, 3, 4, 5, 6, 7, 8, and it will have one blank space. Supposing if you are using BFS alone, the agent tries every possible tile move without any sense of whether it is going closer to goal or it simply got stuck in the loop. So if we talk about the limitations, when you are having no knowledge about the domain, this blind search agent will become extremely slow on large state spaces, no ability to prioritize promising paths. It may explore millions of useless states before finding the goal. So, if the knowledge is equal to 0, then your cost is equal to very high. Okay. Now, we will talk about the informed search. So, lastly, we talked about the blind search agent. Now, we will talk about the informed search agent. So, in the beginning, we were talking about this only. So, we will talk in detail about this informed search. Okay. So, this informed search agent will have partial domain knowledge, and it also uses something called as a heuristics. What is a heuristic? And heuristic is nothing but it is an estimate of how close any state is to the goal. So it does not guarantee to be perfect, but it is a guided search in the right direction. Okay. Now, how do we write this heuristics generally? If I'm going to take I mean the A star search, I will write f of n is equal to g of n plus h of n. Okay. Here, this h of n is the heuristics. It varies. Suppose if I'm going to use A star, I'm going to use this. If I'm going to use best first search, BFS, then I can talk only about h of n. Okay. So this will help us, this heuristics will help us to estimate the cost from node n to the goal node. So the agent uses this heuristics value to prioritize which state to explore next. Okay. So, but it does not guarantee a perfect solution, but it will guide you to the goal and the search becomes automatically efficient. So, what are the algorithms that are possible? First, we can talk about greedy best first search. So, this will try and always expand the node that's really closest to the goal according to the value of h of. But it does not guarantee to give you an optimal solution. It might take a promising path towards your goal. Even might be it's a very big path, but it will take you to the goal, but it's only based purely on this value. So whichever is nearly closest to the goal, it will choose that state to expand. But when we talk about the A star search, it combines this G of n plus h of n. Okay. This g of n is the path cost, h of n is the heuristics. Lastly, we talked in the previous session, we talked about the route finding problem, wherein we had about the problem of going from city Bucharest to Arad. So every city in between had the heuristics of the distance as its heuristics. So the combined score of this f of n gives us an optimal balance between where we are expected to expand the solution. So generally this A star is optimal and complete. Suppose if you take the 8% problem, there are two popular heuristics. One is the misplaced tiles. Means count how many tiles are not in their goal position. So you might be given an initial initial tile position, and then you might be given a goal tile position. So automatically, already you know the goal tile position. That is your tile should be arranged in 1, 2, 3, 4, 5, 6, 7, and 8. This is your goal. The initial state might be anything. Okay. You can use the misplaced tiles to identify it. Another one is the Manhattan distance. So it sums up how far each tile is from the goal position. So it is measured as the number of steps up, down, left and right. These are the directions. So it is more informative and leads to faster and efficient search. When you have some kind of heuristics, even if we have the knowledge, partial knowledge about the domain, your cost will be significantly reduced. Okay. Now we'll talk about this deep knowledge. Okay. So what is this deep knowledge? So we have seen in the previous slide, we have seen what is a deep knowledge. Okay. Here, the agent has rich domain knowledge, but it knows the facts, rules, constraints, and inference mechanisms. How it works? The agent does not search, it reasons. Very important. Rules and facts allow the agent to deduce answers directly. Large portions of the search space are eliminated through logic, not exploration. Very important. We saw the example of Marcus. We'll see it again here, once again. So when we take the famous Marcus example, so already we have said the agent has the facts and rules and constraints and inference mechanisms. So what are the known facts? Marcus was a Pompeian. All Pompeians died in 79 AD. It is now 2024 AD. No mortal lives longer than 150 years. Now it has to answer whether Marcus is alive or not. The agent does not search through all people who ever lived. So this deep knowledge replaces search entirely. So from this available facts, based on the logic, it will conclude that no mortal is more than 150 years, so Marcus also will not live now. Right? So what are the algorithms and techniques that can be used? So you can try knowledge-based systems, constraint satisfaction problems, logical inferences. You can use forward chaining, backward chaining. Then you can go for expert systems. So when you have deep knowledge, your search is going to be minimal or eliminated directly. Means you arrive at the solution through logical inferences. Next, we'll take this Marcus problem. Okay. We'll see how the knowledge plays its role. Okay. We'll take the Marcus problem and see how it is working with all these three. Okay. Now, if you talk about the agent must answer the question, is Marcus alive? So we know three types of knowledge, like with no knowledge, with heuristics, and the deep knowledge. Supposingly, if the agent has to answer this question, is Marcus alive, with no knowledge, so the agent would need to search through all historical records, all possible people, and all time periods. So it's computationally impossible. We cannot find. It's a very long time. No solution is reachable in practice. Supposingly, with heuristics, you have partial knowledge. You have some facts. The agent knows roughly that ancient Romans are unlikely to be alive. So, when you have some kind of information like this, your search gets significantly narrowed down. But it's not a proof still. But it's again a strong guess based on this fact available. Suppose if it is a deep knowledge based agent, then it knows all the rules about Pompeii, mortality, and lifespan. They are applied directly. So, definitive logical conclusion that Marcus is not alive. It's a proof. No search is required. It's pure reasoning. So, what we conclude is the role of knowledge is to replace search. Very, very important topic, right? So, when you have more knowledge, less search is needed. Okay. So, to make you understand and feel the difference, I've just taken this example. Now, we have talked about like the problem of Marcus. Now we will see the same in different problem types. Suppose if you take a root finding problem. So if you have no knowledge, again you have to try all possible routes. Supposing if you have some heuristics, then you're going to use some informed search strategies. So you can use the straight line distance to find the goal. So definitely if you are going to use an A-star algorithm, use the evaluation function f of n is equal to g of n plus h of n, which will help you to find optimal routes definitely or efficiently. Suppose if you don't have any heuristics, uniform cost search try to explore in all directions equally. Again, that's going to be very slow and very costly. Next, if you take the problem of 8 puzzle, if you have a heuristic knowledge, that is your Manhattan distance or the misplaced tiles, so it will reduce your state space so that you can try to get your solution. If you have deep knowledge of tiles pattern, you can pre-compute the solution databases. If you talk about the problem of chess, if you have the heuristic knowledge about the piece values, that is the coins, the board control, king safety, then the algorithms like Minimax with alpha beta pruning uses to cut the search space. You can prune certain search spaces which are not going to lead you to the solution. Okay. So by using these kind of alpha beta pruning, eliminates the search entirely for known positions. So when you talk about this medical diagnosis, if you have a deep knowledge about the symptoms, diseases, drug interactions, you can use expert systems to apply the rules directly. So you don't have to go and do the exhaustive search through all possible diagnoses. So here the knowledge is the solution to the mechanism. Okay. Now We saw that we'll see one more example now. Suppose if I have no knowledge, I'm going to go with blind or uninformed search strategies. The agent has no idea which direction is better. Already I talked about this maze game, right, at the beginning. So what the agent will do? It will start, no map, no hint, no sense of direction. How it will try? It will go to left, dead end. It will try right, dead end. It will go straight, dead end. So like this, it will try and search your full uh, maze. Okay. So again, you'll have to backtrack, come and try another path. Okay. Suppose if you're going to use for the same maze game, if you're going to use the breadth first search. So how it will find the path? It explores all paths level by level. Okay. It will start splitting to A and B. After this, it will again start to split further C, D, E and exit. So for sure, it will have the shortest path, but every node on every level must be visited. So how is the order of execution? It will start, it will go to A, it will go to B, it will go to C, it will go to D, it will go to E and finally exit. So it explores every room on floor 1 before going to floor 2. Now this is floor 1, this is floor 2 means in this floor it has to explore both A and B. So naturally this is a slow solution and it checks blindly. Now for the same problem, if I apply DFS, depth first search, it goes as deep as possible down one path before tracking. It goes deep. Same maze layout, start, it splits into A, B, splits to C, D, and then exit, suppose. So what is the order? It will start, it will go to A, it will go to C. It's a dead end, there is no exit. It will backtrack, then it will come back to D. Again, there is no exit. Backtrack, then it will come to B, this side, right hand side, then it will find the exit. So, since it's going deeper, suppose my solution is here. If I go here and completely search, here it is a very small tree. If I have a very big, deeper branch, then what will happen? So, it might miss the node at the shortest level. But it uses less memory. Its advantages, but also its disadvantages. Supposing if I take for the same problem the uniform cost search, explores a path based on lowest total cost so far. Still no goal gauge. So how it will do? Same it will start from go to A. Here it is cost is 1. From A to C the cost is 2. Again it will backtrack. From start to B the cost is 5. Then from B to the exit is cost is 1. So UCS always picks the cheapest frontier node. So it finds the way. How does it find the way? A to C at a cost of 3. A to C at the cost of 3. Before considering the exit at B, which is at a cost of 6. It is cost aware but still no knowledge of where the exit is actually available. So all three works like PFS, DFS, UCS, but without any knowledge on the goal. So the consumption is enormous. So we have talked about without knowledge, right? So now we will talk about with knowledge and see how the agent is going to work. We're going to take the 8% problem as example. So the heuristics we are using here is Manhattan distance heuristics. Okay. Here, what we'll try and do, we'll try and solve this. Okay. Right. We'll try and do it step by step. Okay. Now, here, the start state is actually, if you see, it will go like this, like it is 0, 1, 2, just for the position, how will you do it? 0, 1, 2. Same for the goal state. Now, how it happens? It reads row by row. It will go 1, 2, 3, 4, 5, 6, 7, 5. 4, 5, 6, 7, 8, 9. Okay. So, but here we have only till 8 and this has to be left as blank. Okay. Now, this is one of the initial state or the start state. Anything it can. Okay. This is the last or the goal state where we have to achieve with a blank at the end. Now, when you compare the two grids carefully, so you can see what are the tiles in the initial state that are matching with your goal state. Okay, that's very important. You can see 1 is at the same place, 2 is at the same place, 3 is at the same place, 4 is at the same place. But you can see 5 is misplaced. 6 is same, 7 is same, but 8 is misplaced. So meaning 1, 2, 3, 4, 6, 7 are already in their correct positions. So we have only 2 tiles that are out of place. So 5 is currently sitting at row 2 in column 1. Row 2, column 1, 2, comma 1. In the goal, actually it is sitting here, 1, comma 1. So tile 5 needs to move. Okay. Similarly, if you take 8, 8 is currently at 2, comma 2. Second row, second column. But at the goal, it should be second row, first column. So this also has to be moved. So the two tiles out of place, each one step away from the goal. So this is our starting problem. Now A star, because it's with heuristics, right? With knowledge. So A star needs to find out that systematically. Okay. Now we'll see how to do it. So first step is we will talk about two parts, defining the heuristics and then we'll do the computational table. So defining the heuristics, we are using Manhattan distance. For every tile, Manhattan distance asks what it asks. How many steps would this tile need to take to go to the goal state? So you can move up, you can move down, you can move left or you can move right to reach the goal. Then we add up all those distances across all the tiles. That will be your h of n. Okay, understood? Right. Now we will compute h for the start state with the given initial position. So you want to take this initial position, you are having a blank at the middle. Okay, right? So if you take the tile 1 is at position 0, comma 0, its goal is 0, comma 0, the distance is 0. If you take tile 2, it is at 0, comma 1, that is row 0, column 1. In goal also it is at row 0, column 1. So distance is 0. If you take tile 3, row 0, column 2, in goal also row 0, column 2, distance is 0. Similarly, if you take tile 4, it's at row 1, column 0. Here also it's row 1, column 0. When you take tile 6, it's also at row 1, column 2. Here also it's row 1, column 2. If you take tile 7, it's at row 2, column 0. In goal also it is row 2, column 0. So you don't have to calculate any distances here. Now we have to bother about only the two tiles that are misplaced. So you'll add 0 plus 0 plus 0 plus 0 plus 0 plus 0. Now if you take the fifth tile is actually, if you see, is at row 2, column 1. Fifth tile is at row 2, column 1. Now, actually, its goal is row 1, column 1. Okay. So, you will take the difference. So, you can take the difference. Okay. As 2 minus 1 is equal to 1. This is the row difference. I'm talking about the row difference. Similarly, you take the column difference. It's 1 minus 1, which is equal to 0. Okay. So total distance for the tile 5 is 1. Okay, that's what you have written here. Similarly, if you take the tile 8 is at row 2. So maybe I'll write it for you here. Wait a minute. 0, 1, 2, 0, 1, 2. Now where exactly is that 8? 8 is at row 2, column 2 here. This is at the starting goal. Okay. So the goal is actually at row 2, column 1. This is the goal. This is where the 8 has to be there. So again, you find the row difference. When you find the row difference, it's going to be 2 minus 2. And column difference is 2 minus 1. So it's 1. So when you add all these things, that's going to be 2. So if you take the g of n, what is the formula for evaluation function? F of n is equal to g of n plus h of n. Here h of n is 2 and g of n is 0. So 0 plus 2 is 2. So now the cost to reach from start to start is 0. That's what we're going to start as 0 here. Okay. So therefore, we are having the evaluation function to be 2. So total cost of the best solution through this node. Okay. So with this we begin. So this is how this is calculated with the misplaced tiles. Now we'll talk about the generating the possible moves. Okay. Here, what moves can we make from the start state? Okay. The blank tile. Where is the blank tile? The blank tile is at initial. I'm talking about the initial thing. It's at row 1, column 1. Maybe I can write the initial state. This is your initial state. 1, comma 1. This is your 1, 2, 3, 4 space 5. 4 space 6. That's your initial state, right? Wait a minute. I just find this. Okay. So we can find this 1, 2, 3, 4 space 6. Okay. So is that row 1, column 1. Here only your blank space is available at the initial board state, the grid center. So from the center, the blank can swap with the tile. I mean, if the blank is here, so it can go anywhere. Like it can swap the tile above it, below it, to its left, to its right. So this gives us exactly 4 possible moves, 4 child states. Supposingly, sorry, if I move the child upward, like 1, I already said 1, 2, 3, 4, 6. Here is the blank space, right? If I move the tile upward, the blank is in the middle here. Okay. Tile 5 is directly below the blank. Okay. Okay. When tile 5 slides up, it takes the blank space and the blank drops down. The result is 1, 2, 3, 4, 5, 6. Bottom row is 7, blank 8. Okay. Tiles 1, 2, 3, 4, 5, 6 all are in correct position now. Only tile 8 is misplaced. Now supposing if I move tile 8, I mean this 8 left this side. So what happened? This moves, blank moves here, right? So when the tile 8 slides left, the result is 1, 2, 3, 4, 6 and the blank will be here. Bottom row is 7, 5, 8. Tile 6 has moved out of the place if I try and do this. Tile 5 is still out of place. And tile 8 is still out of place. This move, yes, because here there should be only blank, na? Everything is out of place. This has made things worse. Suppose if tile 4 move rightward, tile 4 is left to the blank here. Because initially the blank is here. Na? If this goes here, top row is 1, 2, 3, middle row becomes blank 4, 6 and 7, 5, 8. Again, tile 4 is now out of place. Tile 5, tile 8, all are misplaced here. Again, this is worse. If you talk about the tile 4, I mean, the next movement, possible movement is 2. Suppose 2 comes here and blank will go up. 2 tiles down, I mean, move 2 tile downward, the blank will go here and top. Top row will be 1, blank 3, middle row will be 4, 2, 6, bottom row will be 7, 5, 8. Now tile 2 is again out of place. Still 5 and 8 are misplaced. Again it's worse. The question is, A star now asks, which of these 4 looks better or promising answer? Okay. Now we'll see how to do that. So to compute, we use the A star search. F of n is equal to G of n plus H of n. So we take G is equal to 1. For all children, because we have made exactly, every time we try to make one move. Okay, we'll start with child A. Okay. So, move 5 up. The grid is, how the grid will look? 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, blank and 8. Okay. Now we're going to compute this h of n. We're going to compute the h of n. Tile 5 is now at row 1, column 1. Correct. Its Gold row is row 1, column 1. Okay. So, distance is equal to 0. Tile 5 is solved. Now it's a correct position, goal position. But if you talk about the tile 8 is at row 2 here. It's misplaced. Its goal is actually row 2, column 1 here. The goal is here for 8. So difference is 1. Okay. So your h of n is 0 plus 1, that is 1. Already you know g is 1. So f of n will be 1 plus 1, 2. Now we'll talk about the second move, that is move 8 left. How will your grid look? Your grid will look 1, 2, 3, 4, 6. Your blank will be here, 7, 5 and 8. Now, if you take this tile 8 here, okay, is that okay? Row 1, column 2, right? So, actually the goal for the, I mean, if you move this here, then position is going to change. Suppose the goal position is here, 8, okay? Okay. The difference is going to be for tile 8 is 2 and for tile 6, because all are misplaced, 1 and for tile 5 it is 1. So, your h of n becomes 2 plus 1 plus 1. Okay. We are doing the column and row differences. So, f is going to be 5. Now, when we talk about the child C, moving the tile 4 rightward. Okay. So, what happens? So, the goal is that if you move, if the tile 4 has moved from row 1, column 0 to row 1, column 1. Here. So 0, row 1, column 1 here. Then you try and calculate the misplaced tiles. So it will be like the difference is 1 between the state and the goal. Okay. Right? So already we have the existing 2 tiles. Misplaced tiles is 5 and 8. So it's still 3. So our F will be 4. Okay. So similar procedure only you have to follow here also. So when you talk about the child D, move 2 downwards. If you move downwards, the grid will look like 1, blank, 3, 4, 2, 6, 7, 5, 8. Already we have a lot of misplaced tiles, right? 5 and 8 are already still misplaced. Okay. So again, if you calculate the misplaced tile, the value is 1. Already 5 and 8 are misplaced. So the value is again 3. So total F is 4. Okay. Child A has F equal to 2. And if you see here, F is equal to 5 for B, and for C it's 4, and for D it's 4. So A star always picks the node with lowest F value. What is the lowest F value here? Only the child A with equals 2. Okay. So child A is expanded next. So at step 5, we select child A. Yes, with F has the lowest score, and you expand it. Now your board position is like this: 1, 2, 3, 4, 5, 6, 7, blank 8. Now only tile 8 is misplaced. So the blank is at 2 comma 2 comma 1. So what are the possible moves? I can bring 5 here, I can take 7 here, I can do 8 here. Suppose move 5 downwards and take this, we can do, but 5 is already visited. So generally we have to avoid the visited states, already visited states. So we'll go to this 7. So what is the possibility of 7? Move tile 7. The blank will go here. So the board position will be like this. Blank 7 and 8. But still, again, this is a misplaced portion. Okay. Now, 7 is also have become misplaced. 8 is also misplaced. Again, this is misleading because of it's away from the goal. Now, if we move this 8, okay, here it is. If I move the 8 here, leftward, and the blank moves. It's like 1, 2, 3, 4, 5, 6, 7, 8 blank. Now, this is your goal state. Okay. So, we have tried all the possibilities and finally, not all the possibilities, with the help of the heuristics, we have tried to make the moves and finally the goal is achieved. Okay. Here, if you see, when you try and compute the goal child, so h is equal 0, g is equal to 2 because we made 2 moves. So, if you add both, we get 2. And we have to do the goal test. Again, f is equal to 2 is the lowest in the frontier we have observed so far. And h equals 0. So the goal is reached. So there is no remaining distances to the goal. So the goal test passes. So search is completed. If you trace back the solution path, A star maintains the parent frontier pointers. So we can work backwards from the goal to the start. Parent child is A. Goal state parent is A. A's parent is start. So we have done these two tile movement to achieve the solution. So two moves are made that has given the optimal solution. So a lot of discussion happened. I tried to solve one and same procedure we can solve the others. A star with Manhattan distance solved this puzzle in two moves, expanding only two nodes beyond the start. Supposing if because of the available heuristics. If you use a blind BFS on the same puzzle, might expand dozens or even hundreds of nodes before finding the answer. The heuristics used is Manhattan gave the agent the knowledge about how far is the goal. So how many tiles I have to move, how many positions I have to move. So this guided knowledge was very helpful for the agent at each step. So A star tried and picked the most promising node. It never wasted on states that were worsening or away from the goal. So this is the power of the informed search. So role of knowledge with respect to agent is very, very powerful. So deep knowledge or the heuristics will make the agent more intelligent and behavior possible. So this was the most technical lecture, I think, most of solving things. We talked about a lot of F value, G value, H value. Okay. Right. Now, what we can do here is the references I followed was the same Stuart Russell, Peter Norvig, Parag Kulkarni, and Ella Heinrich. Thank you.